Hi everybody, in this video I'm going to talk about irreversible versus reversible reactions. And these are going to be, we're going to see the differences here when we talk about the difference between strong and weak nucleophiles. So far all of the carbonyl reactions that we've been talking about have mainly been with strong nucleophiles. So that's things like the C- that we have, or the H- that we have. You know, the C- is going to be any of our organolithium or Grignard reagents. Okay, so any of those are going to be strong. And then for the hydrides, we're looking at stuff like lithium aluminum hydride or sodium borohydride. Okay, and those are all going to be the strong nucleophiles, right? They are pretty unstable, they're very reactive, and they're going to head right for those ketone electrophiles. So think about strong nucleophiles, they're all charged, pretty much. That's kind of what we want to be doing as the takeaway here. So for weak nucleophiles, we again can kind of think back to our SN1, SN2 days, where we're looking at charged things mainly for the strong and neutral things mainly for the weak. So these should be pretty similar to you, pretty familiar in that way. So for the weak nucleophiles, we're really looking at neutral compounds. So we could have alcohols, we could have primary amines, or secondary amines. Okay, so think about these. These are going to be neutral oxygen and nitrogen nucleophiles. Okay, so strong versus weak. Weak is going to be our neutral things, alcohols, amines. Strong is going to be our charged species, C-, H-, those types of things. Okay, so if we look at the actual breakdown of what these two reactions look like, and why one is reversible and one is irreversible, it helps to look at the reaction coordinate diagrams a little bit. So if we look at the reaction coordinate diagram for the strong compounds. So what we've been doing, these are the reactions we've been doing so far with the Grignards and the hydride reagents and all of that stuff. If we're looking at the energy of the starting materials, so we're going to have, just label my axes. So our starting material, I'm going to label that as SM. So that's going to be our carbonyl plus our nucleophile. Okay, so starting materials, plural. So our carbonyl plus our nucleophile. The carbonyl is not high energy, but if we're looking at the system on the whole, our nucleophile is very high energy because carbon doesn't want to be negative, hydrogen doesn't want to be negative. So those are very high energy starting materials. So overall, we're starting up pretty high just on the basis of the nucleophile alone. Okay, so then we can get down to some nice product where, think about what you're switching when you do a Grignard reaction. You're starting with a C- and then you're going to an O-. That is a lot lower energy. That oxygen is nice and electronegative. It's pretty good at handling that negative charge. So when you go through this, you're going to go through an energy of activation. Oh, let me try that again. So we go through energy of activation and end up at the product. Okay, so we've got a high energy C- or H-, and then we go down to a low energy O-. Okay, so this is irreversible. Okay, because it's saying that when we get to that product stage, yes, we had enough energy of activation to get through this energy hill, but we don't have enough to get through that energy hill if we were trying to go that direction, going from products to starting materials. That process is what makes it a reversible reaction. So if this is irreversible, we can't go backwards. Okay, so products do not go to reactants. Okay, we get a big old X there. So once we hit products, we cannot reform that carbonyl again if we're trying to kick off a C- or an H-, right? And this is very different than like an ester addition or something like that, where you're kicking off an oxygen leaving group or a chloride leaving group. We're talking about if you're trying to get back to the carbonyl without a leaving group, like say you're adding to an aldehyde or something. You cannot do that because this energy barrier is going to be too great to overcome. So let's just write that down. Energy difference is too great. Okay, so if we just kind of label this, this is the EA starting material to product. Whereas this one would be EA product to starting material. Okay, much, much larger. So if we look at the situation where we've got a weak nucleophile, okay, so if we look at our reaction coordinate diagram here, if we're starting out, actually, let me try to reach that down just a touch. So if we're starting out, we're looking at where our starting materials are going to lie on this reaction coordinate diagram. Our starting material on the strong nucleophile was way up high because the nucleophiles are high in energy. But if we have any of these nucleophiles, those are pretty stable. Alcohols are pretty stable. Amines are pretty stable. So they're neutral. They have all the electrons that they want. They're not charged. Everything is right in their world. So when we get to that situation, our starting material is much, much lower in energy. Okay, and it's actually not that much different from the product energy. So then when we have the starting material and the products at very similar or similar energies, then it means that the energy of activation is the same-ish for both, okay? So we don't have a big discrepancy between one side or the other side in terms of how much energy the system needs to be able to go through them. So this is going to be reversible. So we can go backwards from products to reactants. Okay, so there's actually a special arrow that is used with these, and we've seen that arrow used before in acid-base reactions. It is the equilibrium arrow. Okay, indicating that we can go back and forth from products to reactants as we want. So we're going to have to learn specific ways of how the reaction should be run to enable us to get one product over the other one, to make sure that if we're trying to get everything to product, how are we going to do that if I have a dynamic equilibrium going on here? So we're going to need to change the reaction conditions to favor the starting material or the products. Okay, so one thing that's going to be really, really helpful for us as we go through this is remembering Le Chatelier's principle. Okay, and thinking about if there is a product that I can remove from the system, then I can continually make more product and kind of drive my equilibrium in that direction. So by removing or adding reagents from one side or the other, we can kind of help to force that equilibrium towards the direction that we want. So we're going to talk about that and what that really means in terms of the reactions, but I just want to give you kind of an overview of how we want to be thinking about these reactions with irreversible versus reversible, because we are starting to head into that weak nucleophile direction. So as always, let me know if you have any questions, and have a good day.